Sky full of stars, 'cause you light up the path. I don't care, go on and tear me apart.
Okay, welcome to this video on charge, current and potential difference. Just to highlight a couple of the key formulas we need to know at AS and their definitions. So the first one, we can define current as the change in charge over the change in time. What does that mean? It means current is the rate of flow of charge. In an electric circuit in metals, charge carriers are electrons, but we use the idea that charge goes from positive to negative, when in reality it goes from negative to positive. But nevertheless, charge is the flow of electrons. Sorry, current is the flow of electrons, and electrons carry the charge, and that's what we refer to as electricity. So we need to remember the formula I equals delta Q over delta T. Going down, PD. PD is the work done per unit charge. The equation for that defines PD is V equals W over Q, where W is the work done and Q is the charge. So in the case of charge carriers giving up their energy to a component, then it will be work done by the charge carrier. We can also have this as V equals E over Q, which would be energy transferred. In the case of EMF, where a battery is providing energy to the circuit, providing energy to the charge carriers, then it's energy transferred. Work done, also that would be work done in providing energy to those charge carriers. So V equals W over Q. And just a quick note here that's quite interesting. It says here, the rate of flow of charged particles called charge carriers. In a circuit, the charge carriers are electrons, which we just said, but there are other types of charge carrier. So it says in the title here, charge carriers in liquids and gases are ions, so charged atoms essentially. A flow of positively charged particles produces exactly the same current as an equal flow of negatively charged particles in the opposite direction. So that's just talking about conventional current, what we mentioned, conventional current going from positive to negative, whereas electron flow is negative to positive. Not really sure why they mentioned that in terms of highlighting this ions here, but it's a good point that in gases and liquids, we're talking about a flow of ions in those. So uses of ions in air include creating a dramatic backdrop to a Gothic horror story. Okay, so this like lightning is an example of such, of such charge carriers. Okay, moving on. The next equation that we need to note in this section is I equals, and I like to remember it as NavQ. They've put NQVA here, where I is the current in amps, N is the number of electrons per meters cubed, or it says charge carriers here, so number of charge carriers per meters cubed. Q is the charge of the charge carrier, so if it's in a circuit, it's going to be an electron charge, which is 1.6 times 10 to the minus 19 coulombs. V is what's known as the drift velocity, and A is the cross-sectional area of the wire. So let's just quickly read this and remind ourselves what are a few of these terms actually mean. So when current flows through a wire, you might imagine the electrons all moving uniformly in the same direction. In fact, they move randomly in all directions but tend to drift in one way. Okay, so the mean drift velocity is just the average velocity, and it's much, much less than the electron's actual speed. Okay, so the drift velocity is like the velocity of the electrons moving around a circuit, but because they sort of bounce around, then the actual velocity is more than the drift velocity. Let's just see if they put anything useful in this. Here we can see, so N is the number of electrons per meter cubed. So if this is a meter, then we've got a meter cubed, then we've got two electrons here. So if we double the number of charge carriers, and then the current doubles. Okay, so here n, if we double n, then I doubles, provided that Q, V, and A all remain the same. If the carriers move twice as fast, you get twice the charge in the same time, twice the current. So if we double V, what are we saying here? If we double V, then you double I, provided NQ and A stay the same. So doubling the error also doubles the current. Okay, so what we're saying is all these terms are either proportional or inversely proportional to each other, which we know. Okay. Here are some questions. Let's just warm up. Describe in words and symbols how current and charge are related. I equals, what was it? I equals Q over T, isn't it? The definition of current, rate of flow of charge, isn't it? Yeah. So I equals Q over T. Define potential difference. Well, we can define potential difference in terms of the equation we just learned. V equals W over Q. V, potential difference or voltage, is the work done per charge carrier or per unit charge. That's how we say it. Work done per unit charge. And then 3, what happens to the current in a wire if the mean drift velocity of the electrons is halved? Well, we know that what happens to the current in a wire if the mean drift velocity of the electrons is halved? Well, if you halve the drift velocity, then you halve the current because it's directly proportional, provided that all the other variables stay the same. Describe how metals, semiconductors, and insulators differ in terms of N. Well, we didn't actually look at this part, but let's see what it says here. So, yeah, in a metal, charge carriers are free electrons, so N is going to be a lot. And then semiconductors are going to have less than metals, but more than insulators. And then insulators should maybe have, they don't have any. So in an insulator, they don't have any. A perfect insulator would have no charge carriers, so N equals 0. So here it says real insulators have a very small N, because if you put enough current through them, then or enough voltage across them, they can force something to happen. Okay, so here are a few questions at the bottom. I'd just like you to have a go at them, and then we'll go over the answers. Okay. Okay, let's start as we always do, by writing down what we know. Okay, so a battery delivers 4,500 coulombs of charge to a circuit in 10 minutes. So Q equals 4,500 and T equals 10 minutes, but we want that in seconds. So that equals 10 times 60 seconds, which is equal to 600 seconds. Okay, and we know that current equals the amount of charge per time taken. And it tells us to calculate the average current. So we just use this equation and sub the numbers in. Q is 4,500 coulombs, and T is, as we've calculated, 600 seconds. And if we plug that into the calculator, that equals 15 over 2, but we want that in decimal form. 7.5. And the unit of current is amps, so we don't want to forget that. That is the answer to question 1. So if we go on to question 2, a kettle runs off the main supply, and as we're doing it, we want to write down everything that we know. 230 volts, so we know V equals 230 volts, and has an overall efficiency of 88%. Efficiency equals 88%. Calculate how much electric charge will pass through the kettle if it transfers 308 joules of energy to the water it contains. So energy equals 308 joules. And we look here, we've got EV, and we know that V is the work done per unit charge, or the energy transferred per unit charge. And it asks us to calculate, what is it we need to calculate? How much charge will pass through the kettle. So we want to know Q. So if we just rearrange that, Q equals E over V. Now we know we've got a value here for E, which is 308 joules. But that's not all of the energy. There's going to be some, that's the useful energy. So here is the clue, because it's given us the efficiency, isn't it? Yeah? And we know that efficiency is equal to, if I spelled that right, efficiency is equal to useful energy transferred divided by total energy transferred. We want to know the total energy in order to put it into our equation. So we're just going to put total energy, we're just going to rearrange that, aren't we? Energy is going to be useful divided by efficiency. In this case, it's not percent efficiency, it's just efficiency. So the useful is this value here, 308 joules, divided by our efficiency, which is 88%, but we're just going to write it in just the efficiency form, not the percentage efficiency, and then we're just going to calculate that out. So this calculator is a funny little machine. Sometimes it works, sometimes it doesn't. 308 was it, divided by 0.88, and that just gives us the answer there, 350. So the total energy supplied or transferred is 350. It says the useful energy is going to the water, so there must be, what is it, 42 joules of wasted energy, probably dissipated as, I don't know, heat to the surroundings, maybe some noise as well. Alright, so we can plug that into our equation then up here and calculate the amount of charge. So Q equals E over Q. We now have the value, 350 joules, divided by V, which our value is here, and we can calculate that out to get the charge. 350 divided by 230 equals 1.521. So the way we want to write this down is 1.5217 ... and then equal to 1.5, because here is two significant figures, here is two significant figures, so we want our answer also two significant figures, coulombs, and then we can put in brackets two significant figures there. Okay, next question. Number 3. 1.02 times 10 to the 29 free electrons per meters cubed. We know this equation is going to be related to the I equals nav q. That's how I like to remember it. I equals nav q. Okay, so straight away we know that because it was mentioned in the unit, and also here they're saying copper has a number of free electrons, so we know that N equals 1.0 times 10 to the 29 electrons per meters cubed. A is the area, and so forth. Let's see what else it tells us in the question. Calculate the mean drift velocity. So we want to know V. And the cross-sectional area is 5 times 10 to the minus 6 times 10 to the minus 6 meters cubed, squared. And the current is 13 amps. I equals 13 amps. And we know that Q is the charge of an electron, which is 1.6 times 10 to the minus 19 coulombs. So here we want to know V, so we just rearrange for V. V equals I over NAC, big A. And we can sub in the numbers. V, I is 13 amps, divided by, and then just put in the numbers here. N, we've written down 1.0. We're going to put this in brackets. 1.0 times 10 to the 29 times A, 5.0 times 10 to the minus 6 times Q, 1.6 times 10 to the minus 19. Lots of numbers, but don't let that scare you. Just a normal calculation. We could have put the units in, we did on the top, but it doesn't matter when there's a lot of numbers like that. Okay, so here, let's just plug in the numbers. 13 divided by, open bracket. We've got to put the bracket in there because otherwise it's just going to do 13 divided by the first one and then multiplied by. We don't want that. So we don't need to type 1 there, we just put 10 to the 29. 10, where's shift? Tilted the calculator, let's shift. 10, wait, that's not what we want. Don't want shift, we want 10 to the 29, there we go, move it across. Times by 5, we don't need to put in the 0.0, times 10, and then minus 6, and then times 1.6 times 10, and then again minus 19, and close brackets, and that should in theory give us our answer. Again, in physics we always can't leave it in fraction form, so we'll change it to decimals. 1.625 times 10 to the minus 4, and that is meters per second. And don't forget, we need to pay attention to, you know, the decimal places here. This is or the significant figures, 2 significant figures, 2 significant figures, 2 significant figures. We want our answer as 2 significant figures. 1.6 times 10 to the minus 4, 2 significant figures. Wait, I missed out meters per second. 2 significant figures. Okay, and there we go.